Hello friends, welcome to Susan and John MathTube. This is lesson number 13 and we continue with properties of definite integrals. And as always, the 5 important points. Point number 1, 2, 3, 4 and 5. Okay, and with that, let's start lesson number 13. And in this lesson, we are going to do one extra important problem which they always ask in exam. Okay, so please note the question. Prove that integral 0 to pi by 2 log sin x dx is equal to integral 0 to pi by 2 log cos x dx. Of course, this is very easy to prove, it's just one line. But you have to prove that this is equal to the common value pi by 2 log 1 by 2. Okay, so as always, we start with let I equal to 0 to pi by 2 log sin x dx. Okay, and before we start, I'd ask you one question. What is sine 90 minus x? Yeah, sine 90 minus x is cos x. Okay, that's it. So what we do is we apply the property, and we had been applying this property continuously in the last 2-3 videos. That is 0 to a f of x dx is the same as 0 to a f of a minus x dx. So what we do is we replace x with pi by 2 minus x. And what is sine pi by 2 minus x? Yeah, cos x. So this is our equation 1, that is the given thing. And the simplified form, that is the sine pi by 2 minus x will become cos x. And that will give us equation number 2. Anyway, I'm going to write both together so that we can simplify easily. So we have log sin x dx. That is a question. I'm going to call it equation 1. And then I'll write just beneath it 0 to pi by 2. I'll show you what happened here. We replaced x with pi by 2 minus x. So we got log cos x dx, and that is equation number 2. Okay, now look at this. What is log a plus log b? And one important thing, I had been uploading the videos of properties of definite integrals starting from lesson 9, the problems, and the theory on lesson number 8. So make sure you watch from the beginning, because if you watch from the middle, you may not understand clearly. Okay, anyway, what is log a plus log b? Log a plus log b is, log of a into b. And now I apply the usual technique, that is adding the integrals. I'm going to do equation 1 plus 2. So that gives me integral 0 to pi by 2, and I'm going to skip the steps. What is log a plus log b? Yeah, that will be log of a into b. Okay, now observe very carefully. Everything depends on how good you were in trigonometry long back, maybe in class 10. Okay, do you remember the formula for sine 2x, sine 2 theta or sine 2x? Yeah, that is 2 sine x into cos x. Now look at this, I can see sin x into cos x here. So what I do is I multiply and divide that by 2. Now the numerator becomes, look at this, what is 2 sin x cos x? Yeah, sin 2x. So I end up with 2i is equal to integral 0 to pi by 2. I'll show that part once more. Look at this, the numerator becomes sin 2x. So we get sin 2x, the whole divided by 2 dx. Okay, automatically my next question will be, what is log a by b? Yeah, that's equal to log a minus log b. So we get 2i is equal to integral 0 to pi by 2 log sine 2x dx minus integral 0 to pi by 2 log 2 dx. Of course, I skipped a step. First, this became log a by b, that is log a minus log b. And then what I did is I split the integral into 2. Okay, anyway, I cannot do anything with the first integral, so I'm going to call the first integral as I1. I'm going to call the first integral, which looks similar to the question. It's not the question, but it looks kind of like similar. And there's a small difference, that is this 2x. Anyway, log 2 is a constant. I don't know the value. If it is log 1, I'll write 0. If it is log e, I'll write 1. And if it is log 0, I know that it is minus infinity. But log 2, I don't know. It's just a constant. Yeah, I know that it's a constant. And we can take this constant outside the integral. So we get log 2 and then integral 0 to pi by 2 dx. And integral dx is x, you can put the limits. So finally we get 2i is equal to I1 minus, let's simplify that over here. This will become x and within the limits 0 to pi by 2. So pi by 2 minus 0, you're going to get pi by 2. So we get pi by 2 log 2. And where I1 is equal to, what is that I1? I call this as I1. Integral 0 to pi by 2. Yeah, it looks exactly like the question, but the argument is 2x, not x. If this was x, I could have called it as I, because the question is nothing but I. We call the question as I. See, this is the question. But instead of x, we have 2x. So I cannot call it I. Okay, now please call this as equation 1. Keep it safe till we simplify this. Okay, now we will move towards our I1. Okay, so the trick is I put 2x is equal to t. I make a substitution, 2x is equal to t. And whenever you make substitution in a definite interval, you should remember two things. One is the differential. I'm going to take the differential and I need the value of dx. So I'm going to write dx equal to 1 by 2 dt. I'll keep it in a box. And the second most important thing is you have to find the value of t. You're going to substitute. Right now the variable is x, but the substitute variable is t. The new person is t. So this limit belongs to x, but we want the limits for t. So t is equal to 2x. I just read from right to left, but that makes things easier. So now look at this. When I plug in the lower limit, which is x equal to 0, t will be 2 into 0. And when I plug in the upper limit, that is pi by 2, t becomes 2 times pi by 2, that is pi. Okay, so let's substitute right here. And I get I1 is equal to integral t equal to 0 to pi log sine t, and this becomes 1 by 2 dt. Okay, so in the next line, I'm going to write this as 1 by 2 integral t equal to 0 to pi log sine t dt. Now we have to discuss one small property. And if you want to understand that property, you just evaluate integral 1 to 2 x square dx. And then you can evaluate integral 1 to 2 t square dt. And finally you can evaluate integral 1 to 2 y square dy. Here the limits belong to y, here the limits belong to t, here the limits belong to x. Try it and you'll see that you're going to get what's that, x cubed by 3 within the limits 1 to 2. So 2 cube is 8, minus 1. So you get 7 by 3. Again you get 7 by 3. Again you get 7 by 3. And that gives rise to a wonderful property. That is, in a definite integral, the variables do not matter. In a definite integral, the variables do not matter. Only the limit and the function matters. Or this can be done in a proper manner by using the substitute t is equal to x. So that dt will be dx and the limits will remain the same. Anyway, in the next line I'm going to write, because I feel more comfortable with x. So I'm going to write x equal to 0 to pi log sin x dx. What is the reason I am allowed to change the variable? It's simply because in a definite integral, the variables do not matter. But remember, the limits and the function, you are not allowed to change that. Okay, now this looks like our question. I think you still remember the question. I'll show you that question once more. 0 to pi by 2. See, this is our I. 0 to pi by 2 log sin x. The limit is pi by 2. But what did we get here? Oh, pi. But we have a property. Do you remember the property, like suppose you have from 0 to 2a, integral 0 to 2a f of x dx. This can be, suppose you have something like symmetric like this, or if you have something like this, we can apply a property which will cut the limit into the middle. And the property goes like this. I'll write it in the next page. You can note this. Integral 0 to 2a f of x dx will be equal to 0 if f of 2a minus x is equal to minus f of x. And 2 times integral 0 to a f of x dx if f of upper limit minus x, that is 2a minus x, is equal to f of x. This is kind of like the shifted even function and the shifted odd function. Okay, now let's see how this works. So this is 0, this is 2a. And this is the midpoint. So let's imagine a symmetric function. And if it is a symmetric function, when you add all these heights, you get the same height here. So it is enough to add from 0 to a, but you have to double that. At the same time, if the condition is like negative, what happens is half will be above and half will be below. So if you add from 0 to 2a, all the heights you construct here will get cancelled. Okay, anyway, let's try the property here. It's very easy to check. Upper limit minus x should be negative or positive. So what is the upper limit here? Pi. And what is the argument? X. So I just check if log sin pi minus x gives me the same thing or negative or something else. But sin 180 minus x is sin x. Yeah, that means we can apply the property. So I'll write this last step again. So we get I1 is equal to 1 by 2 integral x is equal to 0 to pi log sin x dx. I hope you're doing good till here. And now what I do is, this is 0, this is pi, and the midpoint is pi by 2. And I'm allowed to apply the splitting property. So what I do is, I will add from 0 to pi by 2. And for compensation, I'll put 2 times log sin x. Finally, I get the question. I think you remember the question. This is exactly our I. We call the question as I. This and this will get cancelled, so we get I. So what we just proved is I1 is equal to I. Now I want you to recollect equation number 1. I hope you did note down equation 1. If you want, I will show you equation 1. Look at this. This is equation 1. And what are we trying to find? We are trying to find the value of I. This integral, we called it as I. Okay, so this is equation number 1. Now I'm going to plug in everything in equation 1. So I get 2i is equal to I1 is I minus pi by 2 log 2. And I take it to this side. That means the value of I means the question. This is exactly what we are trying to find. Minus pi by 2 log 2. By the way, there is a property minus log A is equal to log 1 by A. And that gives me pi by 2 log 1 by 2. Okay. This question is really important, so make sure you practice this question again and again till you are really confident with it. Okay, but in the examination, sometimes they won't ask this question as such. So what they do is they change the pattern a little bit. For example, so please note down these questions. I'm not going to work out the question, but I'll show you how these questions are connected to the one which I just did. So one related question is, prove that integral 0 to pi, please note down these questions. You might find the questions in the exam question paper. Dx is equal to pi square by 2 log 1 by 2. So look at this. What we do is we apply the property. I'm going to call it I, and you can see the argument. So 0 to pi x log sin x dx, and I'll call it equation 1 as always. Now I'm going to replace that with pi minus x, and this is just a hint. I'm not going to do the whole thing. So what we get is we get pi minus x here, and sin pi minus x, sin 180 minus x is sin x. So we end up like this. And trust me, when you add these two, we are going to get something like 2i is equal to integral 0 to pi. Look at this. This x and x will get cancelled, and the remaining part is pi. And the pi is a constant, so it will come outside. Okay, we get something similar to the previous question. But just now I told you, this integral 0 to pi log sin x can be split into two integrals, or let's say you need to do only half the job. And we apply that doubling property, that is we multiply by 2 and put the limit pi by 2. Now this is the same as the previous question. Okay, now I'll show you one more related question. Please mark it very, 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 very important, because it doesn't look like the previous question, but this is exactly the previous question. So look at this, integral 0 to 1 log x divided by root under 1 minus x square dx. We have learned long back how to escape from root under 1 minus x square. Whenever we have 1 minus x square, whenever we have root under 1 minus x square, we put x is equal to sine theta. I think you remember that. Okay, so I'm going to put x equal to sine theta. And remember, whenever we make a substitution, we should think about two things. One is the differential, dx equal to a cos theta d theta. And another is the limit. And to find the limit, I have to write theta in terms of x. That is very simple. Theta is equal to sine inverse x. Now these limits belong to x. So when x equal to 0, theta is 0. When x equal to 1, theta is pi by 2. There we go, we get the same problem. See, theta is equal to 0 to pi by 2 log, instead of sine theta, I have to put sine theta. Log sine theta by the denominator will become cos theta. You can try it yourself, and this is cos theta d theta, and we get the same problem. Okay, now I'll give you one more question. I'm not going to work out that problem. You can try. And if you have doubts, you can email me or put that in the comment section. That is an improper integral 0 to infinity log 1 plus x square the whole divided by 1 plus x square dx. And to prove that this is equal to pi log 2, just put x is equal to tan theta. And when you put tan theta, remember this is going to become sec square theta, and the differential will also become sec square theta. So you get log sec square theta, that is sec theta the whole square, and 2 goes here, it becomes log sec theta, that is 1 by cos theta, and log 1 by cos theta is minus 2 log cos theta, and that will be the same question. You try it yourself. I'm not going to spoil by giving you more hint, but if you have any doubt, you can email me or you can put that in the comment section under the video. And please make sure you check my website. I'm putting everything in proper order in the website. You can find the questions very easily in the website compared to YouTube. But at the same time, if you like this and if you find it useful, please subscribe, like, and of course share with your friends. I'll give you one more question. You can try it. 0 to 1 log 1 plus x, the whole divided by 1 plus x square dx. Actually, I did that intentionally. Look at this. This question was 1 plus x square. This question is 1 plus x. This is something else. This is not connected with the previous question. But this is a question which is connected with a question which we did in lesson number 9. And here also you put x equal to tan theta and try it. Okay, I'll be back with another video, and this is the last video in properties of definite integrals. We will be learning improper integrals. So till then, bye.